Here's a lecture for lesson 117, prime and relatively prime numbers and the rational root theorem. So I think we all know what prime numbers are. A relatively prime numbers, what they're talking about is when you have two numbers that don't have any factors in common. So take for instance, well 10 and 14 do have something in common. They have two. 10 and 21, although neither one of them is prime, they are relatively prime. Relatively prime numbers are numbers that when you see a fraction and you can't reduce it anymore, that means the numerator and the denominator are relatively prime. So the 10 and 21, although 10 is not prime and neither is 21, they are relatively prime, meaning that there's not something that goes into 10 that also goes into 21 besides the number 1. Okay, so if you don't really get that, you can read in your book. It's a pretty nice explanation. And then they get to doing a little, kind of a little proof over here, and I'll try to explain it a little bit. You should read it carefully. We don't have to do a problem on this, but this might come up. What it's saying here is that it's hard to read through this thing. What it's saying that is that if you have something, you know, in a factored form on the left-hand side of an equal sign, and then you have two factors on the right, if one of the factors on the left is relatively prime with one of the factors on the right, then the other factor, oh, how can I say this? Let's just read how they say it. Sometimes useful in proofs. Okay, we know immediately that k times p can be written as 5, there's the 5, and then the 2 times 2 times 3, that's the prime factorization of 12. So we know that we could write the left-hand side as just a list of prime factors being multiplied together. Okay, this equal sign says that these two things are getting multiplied together and that they are equal to this. So if the left-hand side, the prime factorization gives us 5 times 2 times 2 times 3, this side better equal 5 times 2 times 2 times 3, or else there shouldn't be an equal sign there. Right? And then if we know that something on the left is relatively prime with something on the right, that gives us, that can tell us something. So let's look at this one. Something times something is equal to negative 8 times q times q times q. Well, I'm just going to hold, I can't read through this iPod, so I'm just going to hold it up here and I'm going to read not through the iPod. It says, if j is an integer and p and q, so if we know that p and q don't have any common factors, then p and q don't have any common factors, so p and negative 8 must. You know what I mean? P must be one of the factors of negative 8 because we have an equal sign here. And so, sorry, I can't read through it. Anyway, read this part very carefully. It says all the prime factors of p and j must also appear on the right-hand side because they appear on the left-hand side. Since p and q have no factors in common, p must be a factor of negative 8. Okay, because p and q don't have anything in common. So p must have something in common with negative 8, or there wouldn't be an equal sign there. Because if I took all the factors of p and all the factors of j and listed them out over here, and then I took all the factors of -8 and q and listed them out over here, they have to be the same for that equal sign to be there. Okay, so you don't have to, I don't think you ever have to even do that proof. But read, you might want to read that carefully. Okay, rational root theorem. It's funny that they didn't give it to you yet, because I think I've mentioned it a few times, and apparently you guys didn't have it yet, but now you do. So when we're doing our synthetic division and we want to decide like what number to divide by, don't I always tell you guys to try 1 or -1? That's because the rational root theorem says that any candidates that might possibly go into, like, say, this quartic here, they have to be a multiple or a factor of 2 over 3. So, like, what you do is you take the constant term, you find all its factors. So the only factors of 2 that I can think of are 1 and 2 and -1 and -2. And then the factors of 3 are ±1, ±3, right? So 1 ends up always being a candidate, and that's why I always tell you guys to try 1, and also same thing with -1. But then after that, like, I wouldn't want to try dividing 2 into this, because the factors of 2 over the factors of 3, well, they don't yield me a 2. So how do we do this? It's pretty easy. I think they call this last number P, and then they call the coefficient of the lead of the highest, they call the lead coefficient Q. So you just get all the factors of P over all the factors of Q. And they explain how to do it. I'm just going to do a problem for you, because I think I don't want to make it more difficult than it has to be. It's really, really pretty simple. So I'm just going to do number 6. Okay, well, number 6, they're just asking, are these two things relatively prime? So I figure out, is there something that goes into both of them besides 1? So the easiest way, maybe the fastest way to do that, is just to, I did an old-fashioned factor tree. I prime factorized 136, and I also did 81 just to check and see if they have any factors in common. So I don't know if you remember how to do this from, I don't know, back when you were a little kid. I like to always do 2's prime, so I always like to keep dividing by 2 until I can't divide by 2 anymore. And then I ended up with 2 times 2 times 2 times 17. Those are all the factors of 136, the prime factors. This one just has all 3's, so I have to say yes, they are relatively prime. Okay, here's rational root theorem. I'm supposed to list all the rational roots. So in other words, all the things that might possibly go evenly into this. So what I do is I take the factors of 5, which are ±1 and ±5. Because I can go +1 times +5 and make 5, or I can go -1 times -5 and multiply to make 5. And then over, I'll make a fraction bar, and then over all of the factors of the lead coefficient, or all the factors of the highest degree term, which is 2, so that's ±1 and ±2. So I know that either +1 over +1, or +1 over -1, or -1 over +1, like any combination of these is a candidate for being able to go into it evenly without a remainder. So I just write that as ±1. And then, but also, any combination of these, like +1 over +2, or -1 over -2, or any combination of these, so we just write it like that. Okay, now I'm done with the 1. I already, paired it with the 1 and the 2. Now 5, any combination of 5 and 1, like 5 over 1, or -5 over 1, or any other combination. I can just write it like this. And then any combination of 5 over 2, ±5 over 2. So if I were going to try to do some division here, these are the only numbers that could possibly go evenly into this quadratic right here. So that's the rational root theorem.